Yeah. Oh, don't worry, I'm in. Thanks. Oh, my mic is on. Read. My mic is on. Come turn it off for me. Oh,
I've been sitting here talking away, and you guys must be watching my lips move.
I assumed you were on the phone because it looked like somebody was talking back, so I just didn't say anything.
I see. So what I had said during all that time was when we started the class, we started by introducing ourselves, which I kind of found interesting because I think since we moved this thing online, we have quite a different group of students than we used to when it was just local teachers taking the program. And so now we're like 3 4 weeks in, depending on how we count, and we've seen like a little bit of the material, at least a glimpse of what will be coming up, right? I mean, this is not a full blown class in anything, right? It's just an intro to a bunch of little topics. But I'm just curious, some of you have I guess what I'd say pretty standard desires from the class, given what we've had in the past, like teaching dual enrollment, improving position in high school and stuff like that. But some of you actually have pretty lofty goals, like going on to PhD programs and teaching at universities and things along those lines. And I'm just sort of wondering if anyone wants to say anything about like still feel the same way, feel like this was a a little heads up to some of the stuff that might be coming? I know I'm sort of asking you, and where you don't really have full knowledge of anything, but just anyone want to make a comment before we jump into actually doing some more math today? Yeah, go ahead, Crystal.
I am still as excited as I was as day one as far as going off for a PhD, but the PhD is not necessarily to become a university professor. It's just for the love of math and learning that I don't know a lot has really just opened my mind and excited me because I mean, I'm on this extreme. I put a joke in my discussion board today saying that, that it's a tangent line about what I know compared to what we've been introduced to. And I'm excited about it. I'm excited about learning. I know it's going to be rigorous. I know it's going to be a challenge, but just the opportunity to continue to grow as a mathematician for me is really what that's about for me. I have no desire to do what you do other than maybe teach college algebra,
Uh-huh.
but I just love the idea of understanding more than what I didn't understand.
Uh-huh. Well, you know what I do a lot of the time is just study math, right? For exactly the same reason. And the more you know about it, the more you know how little tiny itty bitty bit of math you actually know about, right? I mean, there's so much, right? I mean, every time I look at anything, I can go down a rabbit hole instantaneously. I mean, just it's amazing. Yeah, go ahead, Jordan. What do you want to say?
Yeah, no, I just for me, I think I mean my goal is to teach at a junior college, so you don't necessarily need a PhD, but I am shockingly surprised at how much I'm able to follow because that was like a fear of mine.
Mhm.
So a lot of like the undergrad studies is coming back, and just the fact that I'm not completely lost, that I can follow it for the most part, is encouraging for me. So.
Good, good. Yeah, that is encouraging. Yep. And hopefully all of you, no matter what you end up doing, I mean, even when I teach undergrad, basic classes, sometimes questions come up that require some chasing, like I said, chasing down math, down little rabbit holes, and it's amazing how you can end up needing to know quite a bit more, than what you're teaching, at any particular point in time. Yeah, anyone else have a comment along any of those lines? Or, I only get to see one page of you. I get to see most of the class. There's a couple of you like hidden on the back page. I guess LaDonna is kind of hidden on the back page here. Only one person is like not able to fit on the screen. So yeah, Philip, go ahead.
Yeah. Thank you, Professor.
Mhm.
Um, yeah, for me, I've been following the class, and I can really tell that, like Jordan said, most of the my university knowledge started kicking back in.
Mhm.
And then, yeah, I really, really enjoyed the class, honestly speaking. But I'm sorry, I really want to point out something though.
Mhm.
For the topic 4 assignment, I don't know. I couldn't find it. I don't know why. I don't know if you posted the homework, yeah, for topic 4,
Oh, I did.
because I
Yeah.
always, yeah, because I always saw um for the announcement you posted notes on topic 4 and solution to homework 4.
Ah, okay.
So,
So here, I'll share my screen too.
okay.
Let me just get that going. I'll show you. I mean, I think I've been putting them in the same place every week. Um, Share screen. Okay, there we go. Let's see. Sorry, when I share the screen, I have to like move everything around again. Okay, let me move that. Let me move this back up there. Grab this. Okay, so here I'm sharing this now. And so where I've been putting the things are here, right? In the homework for like the topic 4
Oh,
homework form. That's where I've been. That's where I put all the homeworks, I think,
okay.
right? And so there's
Yeah,
the
okay.
homework. And somewhere I even shared the solutions, right? Yeah, there we go, right? So there's the solutions and the notes for topic 4, right? So yeah,
When
so
I
the home
click on the solutions, it doesn't show the solutions. It just brings up the notes on topic 4.
Yeah, they're the same link, but
Oh,
they're
Yeah,
okay.
they're
different.
identical for me as well. There's no
Yeah, they are the
solutions.
same. Exactly,
Well,
yeah.
you guys, well, did anyone tell me that?
Well, you
Don't
said
keep it
that
a
you were
secret.
I
gonna
wanted to answer the
update them in the
questions myself,
announcement, so
so
I just
that's why I
assumed you
didn't
were
tell
updating.
you, because I was ashamed that I even clicked on the link. I'd rather miss it and get better than just copy the answer.
Well, I'm not asking you to copy the answer. I mean, of course, yeah, try it yourself for sure. Um, I was just thinking that today there's a lot of stuff in there that somehow that doesn't look quite right. Let me see. Okay, let me save it. Let me just see. Let me open it up myself and just make sure it's the right link now.
Okay, okay. I've seen it now.
Yep. Okay. So now we have the solutions. Now there was one of the problems in the homework, right? Let's see, where's the actual homework? So now I got to go back and find that again. In the actual homework assignment, one of the problems, the last one, so I guess it's number 5, right, is to go to the AP exam and then look at pick a problem from the AP exam. And it's kind of a fun exercise because some of them are actually pretty good. I mean, even for your own teaching, right? When you look at some of these, some of them are less. I mean, they're all high school level, right? But some of them are less computational and more idea. Like you have to sort of get the idea of what's going on. Like, some of them you want to try to solve without actually having to compute too much stuff, just sort of figure out what they're actually trying to ask. I kind of like those problems, for testing to see if people, there's kind of 2 things you test for often is, can people compute stuff, right? Can you use the rules and compute things? And the other thing is, do you actually understand what you're doing, right? And those are 2 completely different questions, right? And so some of the problems are good. I am going to try to grade. I haven't got around to it yet, but I do want to try to grade, put some sort of grade on topic 3 and topic 4 work. I gave everybody full credit for topic 2 because I just couldn't catch up with that. Once we get today over with, then I sort of through
Actually, you gave us full credit for topic 3.
over one of them. For one of them, I gave you full credit. Well,
Yeah,
what did I do
3.
in topic 2?
You still haven't graded it.
Oh, it's
And
still
I'm
sitting
okay
there.
with full credit for that one too.
Okay. Well, let me. That was kind of a mistake because I get these emails complaining about me not posting grades. I definitely meant to post the topic 2 grades because those are older, right? So those upset the people who are watching. But I would like to give you some feedback, and have it count a little bit, right? I mean, it's fine if everyone gets A's, but it'd be nice to have some differentiation, a little bit for what work's being done. And it's good for me to actually take a look and see what you're doing. Now looking at the DQs, most of the DQs seem to be pretty well answered, right? So I'm not saying anything because everything's pretty much correct in those guys. Now I did add some of my own thoughts to one of the DQs. But anyway, I mean, I'll have everything done. So this class ends on Wednesday. I'm going to give myself at least a week maybe to get everything, polished off. Actually, I'll be in Germany before the end of next week. So before I go to Germany.
Excuse me,
Mhm.
Dr. K. Quick question. This is
Uh-huh.
LaDonna.
Okay.
So I did have a question about that number 5, the one that we have to find our own problem.
Mhm.
My question was, okay, I found my problem, but it's like 3 parts. We have like the A, B, and C, but the only part B is the part I need to integrate the problem to find the infinite number, I think it was. So do I need to do A, B, and C, or do I need to, do I need to do all parts to the question, or just do that one part of this?
So I think I did answer you. That's the one problem I promised not to grade because I can't look at everyone's potentially different problem that you chose, right? But my guess is that A, B, and C are all related. I mean, maybe one part is actually computational, but the other parts are kind of thought related. So it's good to do them anyway.
Okay.
It's good to have access to those and look at them, especially if you teach calculus. I think it's really good to look at those things and maybe even look at them and use them for ideas for problems for your classes even, right? Because there's some pretty decent problems there. Okay, good. All right. Let's see. I guess the other thing I was going to ask, just get some feedback on, is some of you did start using like the HackMD, so you're learning some LaTeX. So Crystal started doing that, and I'm forgetting your name. I'm looking for your name here. Where's your name?
I think you asked me that question. This is LaDonna again. You asked me where did I learn the math, markdown or math. This is LaDonna again. I simply learned that from using your notes, though. I used your notes and just paid attention to what you was typing in. I just went from there and just gave back and forth. So I used all your notes that you had, but you go to your edit part where we cannot edit, but we can still see how you put it in. So I just used that and was able to learn from that. And I just took my notes down and used your notes to help me be successful. I guess that's how I did. Hack.
Yeah, well,
I think that's how.
that's good. I mean, you're learning a little bit of LaTeX along the way, so that's a useful thing. I want to say there's one of you is named Denny, but or Dini, I think. But I don't see you here. I thought I saw her pop in and then maybe disappear again. Maybe she's having some problem. Anyway, one of you, maybe one or two of you got actual like subscriptions, or at least did some work on Overleaf. So, did some really nice looking work there. I forget, one of you actually wrote and said you got a Overleaf subscription, I think. Anyway, I don't know. I mean, but there's lots of little side things, right? You can do. I mean, you've got the math. That's the main thing.
Yes, I paid for Overleaf, but HackMD is a lot easier.
So yeah, I mean, they're kind of used for different things, right? But if I'm making exams or if I'm doing something that looks really professional looking, right, I take it and use Overleaf with it, right? But the LaTeX you're doing is basically kind of the same, right? Anyway, okay, well let's go on to let's see, what do I actually want to do? Because there's so much, I could say so much about this particular topic, way more.
Hey guys, I did add 2 shortcuts that I found that have cheat sheets to help you if you guys are going to learn how to use HackMD. So I bookmarked them on mine if y'all wanted to just take a look at those.
Yeah. I mean, there is like a nice features page that you can open up the source for the features, and then you can see, because you can do lots of things. You can make graphs and you can make flowcharts and embed video. You can do a lot of sort of webby type stuff, right? Can't get too crazy, but you can get pretty crazy with it. Good. All right. So I guess what I wanted to do is I kind of like, let's look at. I've got more notes here than we can possibly make it through. I guess I took Filippo's, the guy who's currently teaching 571. I asked him, like, what should I talk about for for my 2 hours of 571. Oh, there's Dina. She's coming back. Okay, that's who I was trying to remember. Let me let her get back in. Hey Dina, we were talking about you, but you were gone while I was talking about you, so now you're back. Yeah, so what he suggested was like trying to focus on some of the basic things like the extreme value theorem, continuity, mean value theorem from continuity, things like that, in the full context of the way we do it in analysis, right? So some of the notes are about that. So if I just sort of look through the notes real quick, so there's a section on the real number system, which is kind of interesting. We'll talk about it a little bit. There's this little section on continuity and the way that you start dealing with continuity more generally than the way you probably do it in a high school like calculus class. And then the other thing he suggested was talking about the uniqueness and existence theorem for differential equations, which is a fantastic result. But it would be kind of like the culminating result for Math 571. It's got a lot of stuff in there, right? So if you do look at these notes, I mean, this is kind of an outline of the proof. Not every detail is here for sure, right? And then above, I talked some about what closed sets are and bounded sets and compact and connected and the extreme value theorem and the intermediate value theorem. So down here, I highlighted words that are sort of relevant, right, that you can sort of look at. And then below here, I have a little bit on well, no, I don't. So I didn't say anything about uniform continuity, but I have something about uniform convergence. And then there's this theorem, who I don't know how to say, Ascoli Artzrella, I guess is a good guess. Theorem. I know how to use it and look at it, but I don't know how to say it. Anyway, it's a nice result. I mean, there's a lot of stuff in this relatively, really important thing. Like even if you teach differential equations, we've used it already in here quite a bit. You say, I got a second order differential equation. I know that it has unique solutions given two, initial values, right? Or given like 2 bits of data, right? To sort of make the solution unique. How do I know the solutions exist? How do I know they're unique? How do I know that what I have there is a 2-dimensional vector space of solutions? I mean, we've used all that sort of stuff last week when we were doing differential equations, right? Where does that come from? Well, it comes from this analysis class, right? So anyway, it's a nice result, but it really, it's got a lot of stuff. So there's definitely not all the details there. There's just kind of highlighted words indicating things to look for in the future almost, right? But there's a sketch, right? And there's kind of a sketch there, which is, and then to fill out the sketch, I have like a little Now, I know I should probably be doing this stuff with MATLAB, but some things are just easier to do at Desmos. So I have this like little Desmos app thing to look at and play with it. So actually, if I get around to talking about it today, I'll use this app to sort of say what all this kind of crazy stuff I'm doing up here is, right? And at least in that where we can sort of view it and see it. Okay, so anyway, that's the notes, and now for the homework. Here's the homework. The first problem is pretty straightforward, so I'm not gonna. I think, in fact, this could have been like week 1, right? So this is just asking to prove that this, square root of n is basically. I mean, one way of saying this is that for an integer n, square root of n is irrational if it's not a perfect square, right? The way I chose to say it here was that if square root of n is rational, it actually has to be an integer, right? So that's kind of saying things the way you might say them when you're proving certain theorems about, if a polynomial can't be factored over the integers, it also can't be factored over the rationals. There's some sort of nice results like that if it's a polynomial with like integer coefficients. So when you take the algebra class, that's kind of a thing. I don't know really why it's here, except that we talk about irrationals at the beginning of this class, and so maybe that's the reason that this question was here. I did copy these questions from someone else's class, so that's where these questions are coming from. Kind of. I mean, I actually changed a couple of these. The second one's more interesting. Has anyone made a good solid attempt on this second problem? And do you have any
Yes.
what have you come up to? What have you decided the answer is, and what sort of things have you thought about?
I had an issue trying to prove that it was increasing or decreasing. That part of it was hard to me, but I did run into like the Babylonian method. I don't know.
Oh, for finding roots, you mean?
Yeah.
Yeah.
So I ran into that while trying to figure this out. So that was kind of a tangent, but it did kind of apply to this problem. But finding the limit was okay. The issue that I had was proving that it increased or decreased.
Yeah, so I guess that's part of the thing. When you're given a series, right? There's various ways you might, or I guess I should be a little bit careful. This is a sequence. This isn't a series, right? So I guess officially, when we have a series, we're actually summing up a sequence, right? So this is a sequence. We're asking, does this sequence converge? Right, and there's various ways you might try to show that a sequence converges. In this case, there's kind of, I mean, one thing is just, can you figure out if it converges what it converges to? That's pretty easy. Did everyone, or did some of you I mean, before I actually work it, did some of you try that, have a sort of so I mean, just to write it here, right? So the sequence is xn plus 1, and we will use some limit theorem.
Question, Professor K. From my notes, a sequence has a restriction. It has there's a set amount of numbers, and a series is going to infinity. So you said this is a sequence instead of a series. So can you? And I read, I'm kind of confused because I read that in 3 or 4 different places.
So the notation I would use for a sequence, so you can have a finite sequence, of course, right? But we would never talk about convergence for finite sequences, right? Convergence is always something where you're taking a limit, right? So I would write the sequence. Now, when you get into the class, the notation is usually a little bit different, but I would write it as xn. So think of these as being, I'm going to say for now numbers, but later on they would be just arbitrary points in metric spaces or topological spaces or something like that. But for now, I'm going to stick with just R or Rn or Rm or things like that. I'm just going to stick to the kind of the standards, typical spaces you look at in Calc 1 through Calc 3 sort of thing. But yeah, this notation, right, would so typically you could write n equals, and you need a starting point. So just to be specific, I'll say starting at 0 and going through infinity. All right, so sometimes I leave that out. And this is meant to be the sequence x0, x1, x2 forever, right? That's kind of what this notation means. Again, usually I would just leave out those decorations and just write that, right? And sometimes it may need to start at 1 or 2 instead of 0. It depends a little bit on what the the initial conditions are. Typically, these are infinite, right? And the question here is, as I look, if I take the limit as n goes toward infinity, can we tell what xn is doing? Like, is it approaching a limit? Is it converging? Is it diverging? Like, what is it actually doing in this case, right? And there's actually two kind of important things to do here. So one is, you can just say, if this approaches a limit, what does the limit have to be, right? And I think in this problem, I insisted that alpha be greater than 1. Is that what I said? So you have to put some restrictions just to make things act a little nicer. Right? And so given this relationship, if it approaches a limit, can we figure out what the limit has to be? And then, like, what kind of rules are we using to do that? Right? So if it approaches a limit, I don't know what it is, right? Maybe I would like to just figure out what it is. So let's just call it something, right? Let's say xn approaches some limit. I'll just call it L for limit, right? So, I mean, one thing is, like, what does this mean, right? What does this mean to say? Let me just write it out, because this is like week 1 stuff, right? So if I say xn approaches a limit, so that's one notation for this. I could write equivalently the limit as n goes to infinity of xn equals L, right? So those two things are the same in my notation, right? Okay. And then what does this mean if we like write it out using all of our quantifiers and stuff, right? It means that what do I want to say? So for all epsilon greater than 0, I mean, this should start looking very calculusy, right? There exists some, say, n naught, right? Such that for all n greater than or equal to n naught, I'm going to have the distance between xn and L is less than epsilon. All right, like that. So that's, all right. Does that look familiar?
Yes, it does. It looks
Yes,
like
yes,
something
it
I
does.
put in my discussion question.
So then to to prove that it's approaching a limit L, right? One idea is maybe I need to prove this thing. Now that's not what I'm suggesting you do with this particular problem. We're going to use a different result to deal with this problem. But I mean, one option would be, fix an arbitrary epsilon, right? Not your favorite epsilon, just an arbitrary one, right? And then do some work to try to come up with some sort of n, right? This n would be associated to that epsilon. So it'd be like n sub epsilon, for example. You're usually having to come up with some kind of function, actually. And then verify that this property over here holds, right? So that's usually what you'd have to do. Now we're going to do it a different way here that uses kind of more of the structure of the real numbers. But if we were doing an arbitrary sort of convergence in an arbitrary metric space, this is the kind of thing we'd have to deal with, like just right here. Good. I mean, I just wanted to parse this out in terms of the language that we have, right? Now the next thing is suppose, right? So the way that I would sort of suggest doing this one is, suppose that this actually happens, right? So suppose xn approaches L, right? Suppose it does approach a limit, right? Now we have this recursive definition, right? Xn plus 1 is defined as 1/2, and then it's xn plus alpha over xn, right? Given that, right, how can I use this to try to figure out, so now the question is, like, what is L, right? So this is a weird problem in the sense that we're going to show that there is an L without having any clue what it is, right? And then we're going to use this relationship here to actually figure out what the L has to be, right? The thing I probably should have come up with an example where you could try to do something similar and solve an equation, but where there is actually no L at all, right? I mean, so that first step where we show that this does approach some limit is really important here, right? You can't kind of avoid that step. I mean, maybe even that kind of happens if I take alpha to be negative or something. I mean, maybe there's a way of sort of finagling this into an example like that, but there would be better examples. I just don't have one on the tip of my tongue right now. So yeah, I mean, what can I do to actually find L? If I know that L existed, how could I actually find L now, given this relationship? So what did some of you do to find L? Like Jordan, you said you did this. So like, what would you do at this point to find L?
Substitute the
So
x to the
substitute
n
what?
values, the x to the n and n+1 values
Substitute it
to
with
L.
what? Okay.
For L.
So I wouldn't quite say substitute, but what I would say to be more correct, right, is take the limit of both sides. So I'll write this both with kind of this arrow notation, right? So this xn plus 1 is going to L, right? This side over here is going to L plus alpha over L, right? So the limit is that, right?
Right.
That's kind of using the arrow notation. Now, if I just write it out, right, the limit as n goes to infinity of xn plus 1, right? And you got to think about it for just a second. Well, that is actually the same as the limit as n goes to infinity of xn, right? Having the n plus 1 instead of n there doesn't matter. It's still going to go to L. And now here we can be a little bit more specific. The limit as n goes to infinity of 1/2 xn plus alpha over xn, right? Is, right? And now there's these like limit laws. So we haven't talked about that in the class, but any of you who teach calculus have to do this kind of thing all the time. If this thing in here has a limit, right, I can move this scalar outside. So I can say this is 1/2 limit n goes to infinity, right, of xn plus alpha over xn. So if we were teaching, like, this is like the computational part of calculus, right? If you're teaching how to compute using calculus, you learn these limit laws. Like I have the limit of something, I can move the 1/2 out, right? Okay, now I've got this thing which is a sum of two things. Well, if, right, there's an if each of these parts have a limit, then I can actually take this limit out here and distribute it over that sum. So I can get this is 1/2, and then I could pull this in to say limit n goes to infinity xn plus limit n goes to infinity alpha over xn, right? So I'm using here this law that says the limit as n goes to infinity of a bird just flew into my window, which is always terrible, of like xn plus yn, right, is equal to the limit as n goes to infinity. And I'm trying to squeeze this in this little tiny space, and the limit n goes to infinity of yn, right, using, you know, some property of summation, right, to sort of get this, to move this limit from the outside of this thing to the inside of this thing, so to speak, right?
So Dr. K, with the definition that you put above what's at the top of your screen, the limit of an as n approaches infinity equals the limit. Like right above that, I use that kind of definition and then solve for alpha. Does that also work?
Yeah,
Like
yeah. Well, that's what I'm doing, right? But I'm just saying
Okay.
there's a lot of intermediate steps along the way, right?
Gotcha.
I mean, because just writing this isn't, you know, I mean, that's kind of using too much magic to get from here to there, right?
Right.
It's because I mean, it depends, right? It depends on, okay, are you doing this for yourself? Are you teaching this to people just learning limits, right? So let's say you're teaching this to a calculus class, just learning limits, right? So going from here to here is fine. Going from here to here, well, that's really a big jump to just sort of substitute the L's in there, right? We're really using a bunch of theorems that you would teach about limits in order to get there, right? So like we can pull out the 1/2 and we can push the limit through the sum, right? And so I'm almost done here, right? Here I've got a limit of a fraction, right? So again, I can use another limit law that says, you know, I can do this. I'm just wanting to make all this stuff like totally transparent, right? This is like showing all your steps, you know, like that, right? And now once we've got to this stage, right, then I can substitute those L's in there because I'm at that stage where I'm just taking the limit, right? So now I got, you know, this stage I'm at 1/2 L plus alpha over L, right? So I got that. So, I mean, like I said, it depends. If you know what you're doing with limits just fine, just do that in one step, right? You're not really substituting. You really are taking a limit, right? You're taking the limit of the right-hand side. You're taking a limit of the left-hand side. You're not just sort of substituting in, right? So you have to be a little bit careful with the wording there, right? But when you're all done, right, I'm getting that the limit of the left-hand side is L and the limit of the right-hand side is that, right? And now you do exactly what you said. You set them equal to each other, right? And now you just do some algebra, right? And you get, oh no, my silly machine is doing its screwy thing. That's bad. Sorry, my I don't know why, but when I'm got my video going, got all this stuff going, my machine sometimes just causes problems. So let me just let it rest for a second. Anyway, when you solve this, what do you actually get? Like, what do you get for L here?
Square root of A or alpha.
Yeah, so you end up getting square root of A or square root of alpha right up there, right? So this is giving you a way of computing the square root of alpha. Let's see, is this working? Nope. Okay, let me just close this. Oh, one of you might get mad at me for having just done that. Sorry, sorry about that if you do, because it might have just lost all that. Let me see if I can get back.
Dr. K,
Yeah.
in general, would being able to find the limit, would that be proof of convergence in itself?
Not
Does
like
that
what
imply?
not like what we just did. Let me see if I'm back. No, this is still not working. Sorry, let me do this. I'm going to turn off my camera, see if that helps. Oh, that seems to have helped some. So let me just leave. I'm going to leave my camera off because maybe that's causing part of the problem. I think that's what I had. Yeah. Yeah. So what we're doing now, I mean, so the answer to your question is no. You have to be careful, right? We need to show the limit exists first before we just start doing all this computation, right? That's the reason I said it would be nice if I had had an example here where we could do a computation like this, but where really no limit existed at all. I just haven't really thought of, I mean, let's say I had x in, let me just try making up something. Let's say x in plus 1 equals x in plus x in, right? So there's kind of a silly one, right? Now, if you think about it, if I start with like x not being 1, right? So the next thing will be 2, and the next thing will be 4, you know, and I keep doubling it, right? So clearly there's no limit, right? There is no limit, right? Because it would just be blowing up to infinity, right? But if I said now let's just substitute, well, I have L equals, oh, well, okay. Saying L equals 2L is also not a limit. Sorry, I need to, what's something that would almost work here? Well, no, actually saying L equals 2L does give me some, is there a solution L equals 2L? There is a solution L equals 2L. I mean, there's actually kind of two solutions, right? We just said that if we really look at what's going on with the sequence, it's blowing up to infinity, right? So in some sense, infinity is equal to 2 times infinity is true in this sense, right? So you could say that's a solution, right? So, okay, so maybe L is infinity. You ought to feel a little nervous about making that jump, right? So another option here is that L, you know, another solution to this would be L equals 0, right? 0 is definitely equal to 2 times 0, right? So L equals 0 would also be a solution, right? If we just did that substitution and jumped to that answer, right? Now, in some sense, this one's maybe correct, but this one's definitely wrong, right? So this is what I mean by you can't just take this thing and solve and get L equals square root of alpha without also showing that the sequence itself actually converges, right? You need to do that step, right? So that's the thing. And now here we're going to do a little bit. So if we go to the notes, I'm going to say, like, you know, if you kind of look at the notes here, this is kind of in the top part where it's the real number system part, because what I want to do is I want to say this thing has a limit, But for this, we need to actually use a little bit of theory, not just computation, right? And so what I'm going to claim here, and this is where I need the alpha to be greater than 1, right? I want to claim that this sequence xn, is decreasing. By the way, if you wanted to make a guess that that was the case, right? I think I put, let's see, I put this, oh yeah, I made a little like a Desmos thing, right, to look at this, right? So here I'm taking a equal to 8 and just sort of looking at what's happening, right? And clearly this is just decreasing, and it decreases really fast. I mean, if you look at this, let's see, do I actually have the square? Yeah, so the actual square root of 8 is 2.828427, right? And so what I'm showing here isn't those values, it's the amount of error, right? This is the amount of error, right? So the error is, so this is more than cut in half, right? This is more than cut in half, right? So it's actually, I think, increasing by something like 2 digits. It's almost like a logarithmic or like an exponential increase in the number of digits that you're getting correct with every step, right? So not only is this computing the square root of 8, but it's computing it really fast, right? It's still maybe not something you'd like to do by hand, but it's something you could do by hand if you really persevered, right? I mean, when I was a kid, they taught us how to take square roots by hand. I don't remember what they taught us to do, right? But this method would do this, right? It would get us the square root pretty fast, right? The other thing that's good about sort of playing with tools like this is you do get the idea from looking at this that it is decreasing, right? I mean, if you didn't know anything at all, like trying to plot it like this and get an idea of what it looked like is a good idea. It's like a first step of figuring out how I might try to solve this, right? It seems to be decreasing and it seems to be bounded by this line here, which is the bound, right? And after you play with it for a second, you can kind of maybe guess that bound is the square root, right? So it is good to play with examples and look at what's going on, maybe using graphing or something like that to get a feel for what's going on, right? That doesn't give you a proof. It just gives you a feel, right? So that's part of the thing we want to get a difference here. So in the end, I mean, once you sort of get that feeling, we'd like to see that xn is decreasing, and I would like to see that xn is bounded below. Okay, so those two things together. So if I think about this, I've got here's the real numbers drawn kind of up and down, right? And so here's my sequence. Whatever it's doing, it's decreasing, and there's a bound somewhere down here. There's a bound, right? And so the property we're going to use of the real number system, right, is that every set bounded below has a what? What do you think? Like, does it have a greatest lower bound? Like, here's a lower bound, right? Or sorry, let me take that back. Does it have a least lower bound? Let me ask that question first. Like, here's a lower bound. I can clearly find a lower bound, right? So I can find lots of lower bounds, right? So there's no least lower bound, right? But might there be a greatest lower bound? Right? And what do we call this? We call this the greatest lower bound of our set, right? So our set is here, the xn's. It's like in let's say the natural numbers. So this is 0 through infinity, right? Another word we use for this is the infimum of the set. And we could write this as the infimum of xn for n equals 0 to infinity. I mean, there's lots of things you could write here for this, right? But basically we're using the fact that if I have a set A, right? So I have an A, which is a subset of the reals, right? And I've got B, which is less than A, right? So what I mean by this, I mean B is less than any particular element of A. That's what I mean there, right? Okay. If I have those two properties, then there exists an A star right? And we often use this star for like the best something, right? Such that a star is the greatest lower bound. Lower bound. This is like what we had for the integers, where if we had a non-empty set of integers, which was bounded below, remember that? Then we had a least element of that set, right? And that was called the minimal member principle. Something we talked about briefly in the first week, right? And induction is actually equivalent to the least member principle, right? So again, that's something we talked about, the various kinds of induction. That's a property of the integers, right? This is a property of the real numbers. The fact that every bounded set of real numbers, bounded below, has a greatest lower bound, right? That is one of the axioms of the real number system, right? So we're saying, what are the real numbers? This is one of their properties, right? Is it true for Q? Right? Can you think of a subset of Q which is bounded below, right? But where there is no greatest lower bound? Sort of related to the problem we're looking at right now. So if I look at the set of all Q, right, such that Q, sorry, let me take this back. Q in the rationals, right, such that Q squared is greater than 2, right? So this is a set A. It's a subset of Q, right? Is there any greatest lower bound to this thing? So are there lower bounds, for example?
Would it be 0? Because then.
So 0 is definitely a lower bound. So 0 is definitely a lower bound of A, right? Okay. Now, what does it mean to be the greatest lower bound? So here's the set A, whatever it is, A, right? Here's 0 down here, right? What would it mean to be the greatest lower bound? Like if this thing existed, right? What would it mean to be that, right? So
The square root of 2?
so if it was there, it would have to be the square root of 2. That's right, right? So it would be a lower bound, right? And if I took anything bigger than it, right, that would no longer be a lower bound, right? That's what it would mean to be the greatest lower bound. Like what are the lower bounds of this set? So the lower bounds are all these things down here, right? Those are the things that are lower bounds of the set A. Maybe I make this a different color. Let's make A. Let's make A like this color, a little bit wider, right? So what am I doing? Come on, let's do this. So like A will be this kind of red set up here, right? So whatever that is, it's this set here, right? So that's A is like that set right there, right? If I'm looking at the set of all lower bounds of A, that's everything below that set, right? Okay. So the question is right now in Q, is there a greatest lower bound? What would it mean to be a greatest lower bound? It would mean if I took something bigger than that, it's no longer a lower bound. That's what it would mean to be the greatest lower bound, right?
So the highest we could go would be the square root of 2, right?
Yeah, but is the square root of 2 in Q, right?
True.
Square root of 2 is not in Q, right? I mean, that was like problem 1, is that the square root of square root of n is not rational, right? So
then when the greatest lower bound of that be anything, whatever the highest number is, just below the square root of 2?
Well, no, I mean, the point here is that there is no greatest lower bound, right? I mean, in Q, there is no greatest lower bound of this set. So,
Got it.
so,
Okay.
so
Okay,
Q,
now I get it.
Q does not have the property that every bounded set has, greatest lower bound and least upper bound. It does not have that property, right? In fact, if I take Q and I add all the possible lower bounds and upper bounds for subsets of Q, then what I construct is exactly the reals, right? So what that's saying is kind of Q is full of holes, right? So square root of 2 is like a hole in Q. And what determines this hole is that there's a bounded set which has no greatest lower bound, right? There's also a bounded set which has no least upper bound. It would be the set of all Q and Q such that Q squared is less than 2, right? So that would be the set from below which has no least upper bound, right? So there's both those things. And a thing that's kind of hard to get your head around is that there's a whole lot more holes in Q, right, than there are numbers in Q, right? So these are the sort of things you do a lot. And when you do the real analysis class, like the first couple of weeks, you studied this kind of stuff, like what are the real numbers? What are properties of the real numbers? So can anyone tell me like what I mean by that? Like there's a whole lot more holes in Q than there is actually numbers in Q. What do I mean by that? Does anyone know? Like, do you know what saying a set is countable means? I see Crystal shaking her head and muttering something, but no sound is coming out.
I said I'm lost. I'm
So
lost.
This
what does it mean? So a set is countable if it's got the same size as the counting numbers, 0, 1, 2, etc. Right? I told you we can go down lots of rabbit holes in today's talk, right? Because there's just so much stuff. Is Z, the integers, are they countable? They have the same size as the natural numbers. So now Z looks like this: 0, 1, 2, 3, -1, -2, -3. Over here I have the whole numbers or counting numbers: 0, 1, 2, 3. Can I actually come up with a bijection between these two sets?
So when you're saying bijection, are you talking about the fact that natural numbers are nested inside of integers, or?
Well, I mean that's part of it, but and maybe I shouldn't use this symbol. Let me use something like this because I got the minus signs there. I mean,
so
but by bijection,
distance, are you
by
talking
bijection,
about distance?
no, by bijection I mean bijection. I mean it's a function, right? Can I come up with a function going from Z to N, which is 1 to 1 and on? That's what a bijection is, right? 1 to 1 and on to.
So bijection is just another word for function.
No. A function when it's 1 to 1 is called surjective. When a function is onto, it's called, when it's 1 to 1, it's called injective. When it's onto, it's called surjective. And when it's 1 to 1 and onto, it's called bijective. Right? So a bijection is a 1 to 1 onto map from one set to another set. Those are also exactly the functions that will have inverses, right? Because everything will be mapped to, and everything will go to exactly one thing, so you can find an inverse for it, right? So when you're teaching kids like which functions have inverses, like what is the natural log, right? You're looking at the inverse of exponential function, right? You need like the exponential function gives you a bijection between the reals and the positive reals, right? And so the inverse is a bijection between the positive reals and the reals, right? Going the other way, right? E to the x is a function from R. It's a bijection, right? So 1 to 1 and onto. The interval 0 to infinity, open interval 0 infinity, right? And then natural log of x, which is the opposite direction, is a bijection between 0 and infinity. Oops, and it's not closed on that side, it's also open on that side, right? To the entire set of reals, right? But when you're teaching kids what natural log of x is, a very normal way of doing this is to say it's the inverse of e to the x. Which functions have inverses? Well, those functions that are one-to-one and onto, right? Those are usually the ones you say. Those are the bijections, right? Now, when we have two sets and we're saying they're the same size, we're saying that we can come up with a bijection between the two sets. That's what it means to be the same size. I can literally map one-to-one and onto, right, those two sets. So now the question is, can I come up with a one-to-one and onto map of this z, right, with this in? So let me just draw it without defining it. I can map 0 to 0. That's good, right? I can map 1 to, now instead of mapping it to 1, I'm going to map it to 2, right? And I can map 2 to 4, right? So in other words, I can use up the even numbers for the positive integers over here. And then the negative ones, right, I can make -1 to 1, and -2 can go up to 3, right? So I can map the negative numbers onto the odd numbers, right? And so this will give me a bijection between z and n, right? So we can say, the way we write this in set theory is we say z, the size of z, is the same as the size of n. They have the same size, or cardinality is the way we might say that. But what that means is that there's a bijection between the two sets. So kind of up to renaming, these two sets have the same size. Okay. So what about Q? Does Q have the same size as N? Can we just count everything in Q? All right, and now this may be a bit much to, if you haven't seen it before. If you've seen it before, you know what I'm going to do. But I'm going to take like the negative integers here. So I take the entire set of integers there, right? And then I'm going to divide by, so this will be like, so here I'll have 0, 1, 2, etc., right? And over here I'll have -1, -2 going this way. And then here I'll just have 1, 2, so I'm going to leave out 0 in some sense, right? I'm going to have 1, 2, etc. going down this way. Actually, let me pull that off to the side, I guess. So I have down here, 1, 2, etc., right? And then what I want to put here where they cross, so like here, like in the 0, I'm going to have 0 over 1, right? 0 over 2. So this isn't a big array, like a great big matrix, right? But it's infinite dimensional going down this way, and it's infinite dimensional going both of those directions, right? And so here I would have like 1 over 1, right? 1 over 2. So these are my denominators over here, right? I don't have 0, but I have 1, 2, because I can't divide by 0, right? And over here I'll have 2 over 1, 2 over 2, right, etc., right? And over here I have -1 over 1, right? -1 over 2, going down like that, right?
So yes, they have the same size.
So yeah, so it still don't quite see. I got this infinite matrix. Now I'm trying to say the infinite matrix has the same size, right? Now one thing you might want to do is you might want to go through and say, well, look, there's some duplicates here, right? So where I have duplicates, maybe I just cross out the duplicates, right? So there was a duplicate of 1, right? In fact, everywhere along here, I'm going to get a duplicate of 1. And over here, like, well, if I kept going, I'd have 2 over 4, right? So I'd have a duplicate of a half, right? Something like that. So you might go through and cross out all the duplicates, right? But then how can I count them in a way that just uses up the counting numbers? So I can start with this one, call it 0, right? And then I can count, so I'm starting there, and then I can count sort of around in these squares like that, right? And I can count this next one. And I can count this next one. Just using the counting numbers 0 through infinity, right? And I'm always counting a finite set of things, right? These are always finite, but eventually I count everything in this whole array, right? And that would give me a bijection. Now I haven't defined it in terms of giving you a formula. I've just sort of told you how to come up with it, right? If you think really hard, you could come up with a formula for this thing. But what we have here is we then have a bijection f, which I'm defining like this. And I guess I'm doing it from the natural numbers bijectively onto Q, right? So these have the same size. Anything that has the size of the counting.
Colon? Is that F colon natural numbers to Q?
Yeah, that's how we define. Yeah, sorry. So yeah, this is some like when we define a function going from x to y, right? That's the usual way of writing a function, right? From X to Y. Anytime we have a set which is countable, we call it countable. Anytime we have a set which is bijective with the natural numbers, we call it countable. Okay. So the point of all of this is that Q is countable. Okay. There's lots of fun puzzles like this. Like there's this thing called the Hilbert's Hotel. And so you've got like infinitely many rooms, right? Going off forever. You have these rooms, right? And then and all the rooms are completely full, right? And then you have a bus with infinitely many people come up, and it's the job of the manager to now squeeze all these infinitely many people into this infinite hotel. Can you do that, right? And the answer is yes. You just sort of move everybody who was there into the even number rooms, right? And take all the people in this bus and put them in the odd number rooms, right? And you can kind of keep playing this game, and you can say, suppose I had infinitely many buses with infinitely many people show up. Can I fit them all in this hotel? And the answer is still yes, right? So I mean, when you're starting to do infinite math, it becomes kind of strange, right? But all these things are still countable. So countably many countable sets is still countable, right? Q is countable. Okay, so all those. Here's the important one. The important one is that R is not countable. Okay, and the proof that R is not countable goes by a very sort of well-known name, and it's called Cantor's diagonal argument. And it's actually really easy to picture. So I'm going to look at the numbers, I guess, between in just the interval 0, 1. All right, I'm going to show that those numbers are not countable in the reals, subset of the reals. Okay. And so I'm going to do this. And this is going to be a proof by contradiction. I almost feel like maybe I wrote this somewhere earlier in the notes, but maybe not.
Does that symbol say less than or equal to real numbers?
No, this is a subset of.
It's right, the E set.
No, subset.
Okay, thank you.
Right, like that. Yeah. So, and this is a set of, this is all the real numbers between 0 and 1, right? So any real number between 0 and 1, I can write down as a decimal like this. And so like D1, D2, right? So now I'm not using any fancy definition of the real numbers. I'm just using kind of the intuitive grade school notion of real numbers, except that we're really taking for real this idea that there's infinitely many decimal places over there, right? So that's kind of a point here. Suppose that this set was countable, right? Then I should be able to write down a bijection, right? So I could say, here's the first one. Here's the second one. Here's the third one, right? And I should be able to finish out this list and have all the numbers, right? So let's write this down in decimal form. This will be 0 point, and then I'm just going to use like a double index here. This will be D00, right? And then the next digit will be D01, right? The next digit will be D02, but it goes on infinitely far that way, right? And then this next one that I have will be 0, and then D10, D11, D12, going on forever, right? And this next one will be 0 point D, this is 2 here, not 3. 20, D21, D22, etc. Right? So the claim is that, all of the real numbers between 0 and 1 are on this list. That would have to happen if this interval was countable, right? So are we all in agreement about that? If the interval is countable, I should be able to count it, right? So here's a counting of it. There it is, right? But now what we're going to do is we're going to very simply define a new number which is not on this list, right? And it's kind of clear what we're going to do. We're just going to take these digits going down the diagonal. This is why it's called Cantor's diagonal argument, and change each one, right? So I'm going to come up with this number of y, and it's going to be 0 point. It's going to be D00, and I'm just going to put like a hat on top of it, right? So it's associated that. And then D11. So I'm just going down the diagonal, right? D22 hat, all the way down. And all I'm going to do is make sure that D00 is not the same as D00 hat, right? So I've got digits 0 through 9, so I can always do that. Like if D00 is 0, I'll just make D00 hat 1, right? For example, that would work, right? And then I could always just add 1 unless I had a 9, and if I had 9, I would just like add 1 and, I'd make it 0, right? So sort of do like clock addition, but where I'm going around the clock, right? So once I add 1 to 9, I get back to 0 again, right? But whatever, these numbers here are different, right? They're different. This sequence of numbers is not on that list, right? Because if it were on the list, it would be xi, right? And if it is xi, then it would have to be the case that dii, which would be the ith digit of xi, would have to equal dii hat, which we just defined, right? But we just made sure that those two things are not the same, right? So they're different. Okay. So the upshot of this is that the reals are not countable. This is an uncountable set. It's a strictly bigger, so we had all these infinities that might look initially like it may look like z's bigger than the counting numbers, right? Then it may look like q is bigger than z, right? Because they're definitely contain those, but they're actually all the same size, right? But r, in fact, just this one interval, right? Just that one interval is strictly bigger than the counting numbers, right? So it's a strictly bigger infinity.
Dr.
Okay.
K, whose diagonal was that again? What was his name?
Oh, it's called Cantor's diagonal argument.
That gives so much relevance to the movie Divergence and the Cantors.
Oh, well, Cantor is a famous, well, I mean, this is not Cantor like in a Catholic church at Cantor, right? This is someone's name, Cantor. There's a great recent Veritasium. I love this guy's work. I don't know if you guys want to see math presented for the populace, right? He does a great job, and he's got a very recent one on. It's something like the man who broke math or broke infinity or something like that, right? But he talks about this argument there, and so he does this argument again there. But this is a YouTube station, right? So if you go to YouTube and look up Veritasium, you can find this guy's work. And so there's a recent one about this. Now, the point of everything I'm doing right now has to do with the structure of the real numbers. If we have Q, think of Q as kind of looking like a number line. You can't see any holes in Q, right? But we just showed that Q does have holes. In particular, square root of 2 is a hole in Q, right? Square root of 3 is a hole in Q. There's no square root of 2 or square root of 3, but I can certainly look at all the things whose square is bigger than 2 or whose square is bigger than 3, right? So I get these bounded sets that don't have least upper bounds or greatest lower bounds, right? The weird thing is, so the rationals are countable. There's only countably many points in this rational number line, right? All I'm doing is looking at holes between bounded sets, but there are uncountably many holes, right? It's really hard to wrap your head around, right? There are many, many more holes in this line than there are numbers in that line, right? So when I go through and I fill this out by filling up all those holes to get the reals, right? This set is strictly bigger in size than Q, right? So it's really hard to wrap your head around. It's really hard to do a nice proof directly that there are more holes than there are numbers in Q, right? That's the reason I did this diagonal argument instead. You can do something like that with like bounded sets, but it's not so easy to visualize, right? It's really it feels very unintuitive to say, all I'm doing is looking at sets that are bounded. Like, what is like square root of 5? Let me put it here, right? So I'm looking at all the sets, all the elements of Q whose square is bigger than 5, and all the elements of Q whose square is less than 5, right? So I'm just like looking at those two sets. Okay, well, that does define a hole. The square root of 5 is not there, right? But all I'm really doing is like taking a hole and saying, look at the things above it and the things below it, right? you would think there couldn't possibly be more holes there than there are numbers, right? But it turns out that that's wrong. There are actually many, many more holes in Q than there are numbers in Q. All right. So that's an amazing thing about the structure of the real numbers, right? I'm still working on problem 1 from your homework, right? We're still sort of going down a rabbit hole based on that problem, right? In the notes, right, I have this section on the real number system, and I talk about defining the real numbers by these things called Dedekind cuts in Q, right? That's sort of exactly what I'm talking about. Here I'm sort of looking at that. This is kind of what we're sort of looking at right now. It's kind of the first little section of this real number system thing. Going back to our problem now, right? Okay, so I would say, are there any, well, let me just say, are there any questions? Maybe some of you have seen this before. Maybe some of you have a question about what I've done here. This is really kind of vague in some sense. I mean, I've shown you that the reals are bigger than Q, but that's a lot to take in already, right? I want to go back to our sequence, right? So we already know that if this thing converges, then it converges to the square root of 2. Right. So we know that, right? We've sort of done that limit argument to argue that. What I want to do, though, is sort of now say why this thing has a limit at all, right? So that was the next thing, right? And so the claim there was, if I look at this sequence, it's actually a decreasing sequence, right? So it actually is like this, like x1, x0 would be here. And I think in the problem, I just took x0 to be alpha, I think is the way I did it, right? So just say, take that to be alpha. And then x1 is going to be a little bit smaller, right? And so whatever this thing is, it'll be, you know, I mean, literally here it'd be 1/2 alpha plus alpha over alpha, right? That's what it would be there, right? So that would be 1/2 alpha plus 1, right? So you could show that that's smaller. But we want to show in general that these are decreasing, right? So we want to show they're decreasing, okay? And we want to show that they're bounded. Right. And now this is not a completely trivial argument to do. I mean, so I came up with an argument, and in my argument, and even though I'm giving you an argument in these notes, I would say try your best to come up with a different argument, right? See if you can come up with something else, right? In my case, what I did first is I showed, what did I do first? I even have to look and see what I did. Oh yeah, I showed bounded below first is what I did. And I was very specific to show that it's bounded below by alpha. And I think Jordan asked me about this, like you found the decreasing hard to show. I actually use the fact that it's bounded below by alpha to show that it's decreasing, right? So I'm thinking there must be another argument for this, because I feel like mine is really hanging pretty tight on proving a particular thing. Like it feels like there should be another way of doing this. So it would be nice if someone came up with a different way of showing decreasing than what I did here, right? That would be a nice thing to do. But let me go ahead and go through this argument because it's also kind of fun. This is what I mean. This is where you actually have to pull stuff in, right? When you're teaching, right? You might have to pull stuff in from really random places. So all I want to do is show that this sequence is decreasing. That's all I want to do, right? So all I want to do is show that xn plus 1 is less than or equal. Oh, sorry. I want to show it's bounded below first. That's what I want to do first, right? I could try to show it's bounded below by 0. That's easy to do, but that doesn't help, right? So I'm actually going to try to show that it's bounded below. I mean, if this is approaching the limit, square root of alpha, I would definitely expect that it's bounded below by the square root of alpha, right? Now I can't literally say it's bounded below by the square root of alpha because I don't know I don't know that yet, right? So I'm going to show that it's bounded below by alpha squared, right? Is what I'm actually going to show, right? I'm sorry. What I'm actually let me take that back. What I'm going to actually show is that xn squared. I'm going to show that xn squared is bounded below by alpha is what I'm going to show, right? That will show me that xn is bounded below by square root of alpha, right? So I'm actually going to argue about the square of n, not xn directly, right? And here there is some algebra, right? So here's what I do, right? So I'm just going to rewrite what I have in the notes here, right? So xn plus 1 squared, right? So that is, right? So that's 1/2. That was xn plus alpha over xn. Now I'm squaring the whole thing, right? Like that, right? So this is 1/4. And now I'm just going to square this, right? So it's xn squared. Sorry, plus, now when I multiply this thing out, I get what? 2 times this times that. So I will get 2 alpha right there, right? Because the xn times 1 over xn will just become 1, right? Then I got 2 of those because I'm squaring it, right? The 1/4 is just coming from squaring the half, right? And then plus, and this last term will just be alpha squared over xn squared. Okay. And then what am I really doing is I'm really using an induction, right? So I'm saying this, suppose xn squared is greater than or equal to alpha, right? By induction, right? I'm trying to show that xn plus 1 squared is greater than or equal to alpha, right? So I'm actually using induction here for this part of the argument. And the base case, I'm starting at x not equal alpha, is just that alpha squared is greater than alpha, greater than or equal to alpha, right? But my assumption was that alpha was greater than 1. This is why I needed that, by the way, right? So I definitely have this alpha squared is greater than alpha, right? So my base case is okay. I'm assuming I have this at n. I'm trying to get it at n plus 1, right? That's what I'm trying to do. Okay, here's where it becomes tricky, right? Because my assumption is that this thing here is greater than or equal to alpha, right? This is another alpha here, right? So this would be 3 alpha right here. So let me just rewrite this slightly. So one more way. So let me write what I can write, right? I can say this is greater than or equal to 1 over 4. So by induction, I can replace this with alpha, right? Xn squared is greater than or equal to alpha, plus 2 alpha, right? Plus alpha over x1. All right, so I'm sort of in that kind of setting. But this doesn't quite work, right? Because, sorry, not over x1, over xn, right? This doesn't quite work, right? Because xn, we know, is greater than or equal to alpha. That's what we're assuming, right? And so this now is making this less than or equal to 1. Right? It's going in the wrong direction, right? It's not helping us where we need the help, right? Because if I could get that, if I could make that this was greater than or equal to 1, then I've got another alpha and I would have 4 alpha there and I'd be done because 1/4 of 4 alpha would be alpha, which is what I want, right? Okay, but unfortunately, this one term is in the wrong direction, right? So what I actually have to do is a little bit more complicated. So this sort of easy tack just doesn't work, right? And this one makes this problem a little bit fun, right? So instead what I do is I take my original thing. So this was just an equality. So I haven't done any bounding yet. And I just rearrange this sum, right? So I rearrange this in a sequence of steps here like this. So I guess first I just come up with a common denominator. That's all I do first, right? So this is xn4 plus 2xn squared alpha plus alpha squared over xn squared. All right, so all I've done is I've taken this, denominator, right, and made a common denominator. So that haven't done anything except, basic fraction stuff here, right? Okay, but now I can factor the top. So this becomes 1/4 xn squared, and then xn squared plus alpha squared. All right, so like that. And then, okay, so now there's a little bit of trickiness here. I mean, you might try redoing this yourself and see if you come up with another way, but this is what I had to do. I'm going to stick in an alpha here and take one out. So I'm going to have alpha 1 over 4. So up here I have xn squared plus alpha squared over xn squared alpha, like that. So what did I just do there? See that I'm multiplying by alpha and dividing by alpha, right? So that's all I'm doing there, okay? And I'm going to pull out, I'm going to put the 1/4 in there. I'm going to pull out a square, right? So I end up with this thing. So I end up with alpha. So this alpha is going to stay outside. So this is alpha, right? And I'm going to have xn squared plus alpha over 2 squared over, and then down here I'm going to have xn squared alpha to the 1/2 squared. Okay, now the reason will become clear in a minute. This is what I mean by you need to sometimes pull off things. So this is xn squared plus alpha over 2 over xn squared alpha. There's a square root there, right? So like that. And then all of this squared, right? So everything is equality so far. I haven't done anything that's a non-equality in this whole thing, right? So this is just a bunch of algebra up to this point. Okay.
I'm usually really good at algebra, Professor, but I guess there's a step missing in here on how that 1/4 became 1/2, and I understand it.
Yeah, so that one's easy. So I'm just taking this 1/4 and putting it into there, right? So I'm taking, I mean, yeah, so I mean here I can put a little substep. So this is alpha. So this is xn squared plus alpha squared over 1/4, right? So I'm just putting that 1/4 in there, right? Over this xn squared alpha. Sorry, I'm sort of overwriting things here, but that's right. So I really didn't do, I mean, the 1/4 is just going here, right? Just sort of.
How did it change to 2 though?
Because I'm pulling out a square, right? So 2 squared is 4, right? So I'm pulling out this square and I'm taking a square, you know, square there. I'm pulling that square out here, right? Because the goal, I mean,
I see it.
Part of this is I'm using something that I knew, right, already. I mean, I'm trying to get it in this form, and the reason is because here's a fact that we teach, and it's a fun fact to know. This is less than or equal to s plus t over 2. Right, and so one, I could write this as like square root of, right? Square root of st is less than or equal to s plus t over 2. This guy right here is called the geometric mean of 2 numbers, s and t, and they're supposed to be greater than 0. This is the algebraic mean. Now, if you were living in ancient Greece and studying your Euclid, right, there's many, many kinds of means, right? One of them is geometric, algebraic, and there's what is a set of notes is called? The harmonic. There's harmonic means. There's all sorts of means, right? So this relation is an ancient relation between 2 different computations, right? It's an interesting fact, right? That this has been around forever. But I can use that fact here because what this tells me is that this whole thing, right, is greater than 1, right? So this is greater than or equal to alpha times 1 squared, which is alpha. And that's what I wanted to show. Remember, I have equality all the way down here. All these equalities are for xn plus 1. Xn plus 1 equals this thing over here, and that's greater than or equal to alpha. How do I know that's greater than or equal to alpha? Because that ratio right there, right, is greater than or equal to 1, and that's because this is the relationship between the geometric and algebraic means, right? So it's just pulling in this weird fact about math, right, to do a computation here, right, in the middle of what is an induction, right? So, I mean, I'm going to leave it to you to think about some more. I put a link here to the algebraic mean, geometric mean inequality, right? And I've got this stuff. This is the reason I wrote out these notes for the solutions, because it's unlikely very many of you would have come up with that. Now, what I would really like to see is someone coming up with a different proof. That would be awesome, right? Remember, all I'm really wanting to show is that this is descending. I want to show that this is descending and bounded. That's really all I'm trying to do here. And I think I don't know how to spell descending, but anyway, I'm trying to show this descending and bounded, right? Now, what I
Dr.
did,
K,
yep, go ahead.
Since the original equation has a 1/2 on it, couldn't we just use that from the start on that equation?
I mean, you say, can we just? So what I would say is do it, get an actual result, and then send it to me and say, hey, I think I did it some other way. And you can try to show me. It's definitely not decreasing by 1/2 each time, if that's what you're thinking, right? It's going down a little bit, but it's not doing that.
No, I mean, use the that geometric mean thing. Because if we have A as x sub n, and then B as alpha over x sub n as A and B, and then it's divided by 2.
Yeah, that's what I'm doing here, right? I mean, yeah, so the point is, yeah, so here the S is the xn squared, the T is the alpha, right? Same thing down here, right? The S and T, right? So that's the relationship there. I'm not quite sure what you're asking. I mean, I am using that. That was the whole point of getting to it, right? To use it. And I guess I didn't really comment on that, right? So the way it's being used, I mean, just to say this one more time is, I mean, let me just write this one step again. So I have here that xn plus 1 squared is exactly this after doing a lot of algebra, right? So I have this equality, right? That's what I got from all the algebra, right? And now I'm saying that this is greater than or equal to alpha times 1 squared. And now, so what's going on there? So there I'm using the fact that square root of xn squared alpha is less than or equal to xn squared plus alpha over 2, right? And that's because this is the algebraic mean, right, of, so this is the, let me just write the algebraic mean of xn squared and alpha, right? This is the geometric mean, mean of xn squared and alpha, right? And so the relationship between those is that inequality there. So I'm not sure, I mean, that is what I'm using, right, to get that inequality there. I think that's what you were asking, but I'm not quite sure. But anyway, if you see another way of doing it, do it.
I put it in the chat. Like
well, I'm not gonna be able to look at it in the chat, but I mean, write it up and send it to me, and I'll take a look at it and see. I mean, I can look at it in a minute in the chat, but let me finish this argument at the moment. Proving that this inequality holds is also pretty easy. This is really just looking at the fact that, you know, the square is always positive, right? And we kind of do this to it, and anyway, there's a little proof right there that shows that that's true. So that's not a hard thing to prove. It's a very general thing. I mean, so the following thing is also true. Whoops, come back here. Oh gosh, don't do this to me again. I think part of it is that when I use the mouse and, come on. Let me see if it just sort of comes back to life here. Close it again. This is one thing I wish this computer would stop having these troubles. Maybe we could use these troubles to get the school to give me a better computer. Wow, that's a lot of stuff we've done. Okay, we seem to be back. All right. That was the decreasing, right? So by induction, using that argument I just did, all right, we have that that was bounded. I still just have bounded, right? We've shown that the xn is a bounded above, so it's greater than or equal to square root of alpha, right? That's what we've shown so far, right? Now, we already knew that if there was a limit at all, it had to be square root of alpha, right? So we actually did kind of know that in sort of a not unofficial argument, right? Now to show that it's actually decreasing, right? So that turns out to be easy given this particular bound, right? So now I'm just going to compute xn plus 1 over xn. And so this is just 1/2 xn plus alpha over xn, right? Because that's the definition of xn plus 1, right? And so again, just doing a little bit of algebra on this thing, this is 1/2 1 plus alpha over xn squared, right? But we just showed specifically that xn squared is greater than or equal to alpha, right? So this is less than or equal to 1/2 times 2, right? Because this thing right there is less than or equal to 1, right? Because we just got that exact bound. That's the reason I needed that particular bound, right? And so if this is less than or equal to 1, right? In fact, I guess maybe I should have proved straight less than up there. Then that means that this is decreasing, right? Because it's anyway, because that's one way of showing something's decreasing, right? To show that ratio is less than 1, right? So now we have a decreasing bounded sequence, right? And how do we know that that means it has a limit? Well, that's a theorem, right? So here's a theorem you learn, and I mean, it's kind of clear, but in fact, well, let's just prove it. Every decreasing bounded sequence xn has a limit. All right. Well, how do we get this? Well, what we do is we say let L equal the greatest lower bound, or the infimum, of xn. Why do we know that exists? Well, we're in the real numbers. It's bounded, right? So there is a greatest lower bound. We know that, right? That's what we know. Okay. And then what do I know next? Is I know that for any epsilon greater than 0. I mean, now we're going to do a sort of a limit argument, right? If I look at L plus epsilon, well, this is bigger than L, right? This is greater than L, right? So it is no longer a lower bound, right? That was the whole point of being greatest lower bound, right? So what does that mean? It means that, so that happens, so L plus epsilon is not a lower bound. And that means that there exists some n, right, such that xn, this happens, right? So L plus epsilon is greater than xn is greater than L, right? Because that's what it means to, I mean, if all xn's were greater than or equal to this, then it would be a lower bound, but it's not, right? So we're in that situation. But this is a decreasing sequence, right? So in fact, we know that we have L plus epsilon is greater than xn, is greater than xn plus 1, is greater than, et cetera. All of them is greater than or equal to L, right? So in particular, we have there exists an n, namely that one, right? Such that for all m greater than or equal to n, x m minus L, so it's in between these two things, is less than epsilon, right? So the xn's approach L, right? So there's an actual sort of epsilon. I don't want to call it an epsilon delta proof, but it's an epsilon n proof or something like that, right? If you like, right? So there's like a proof that every decreasing bounded sequence has a limit, right? So that's how you would prove that, right? Using the epsilon delta sort of definition of limit there. Okay. And that's all we needed, right? We needed to know that our sequence had a limit. Once we know our sequence had a limit, we computed that the limit had to be square root of alpha, right? But notice that sort of if part, if it has a limit, is really where all the work is, right? That's really where all the work is. So I mean, this is one sort of interesting kind of simple problem that has a lot of side issues to it, which is kind of fun, right? Anyway, I think, right? So these are good problems. We have 30 minutes left. So I would say, let me just ask, any questions about that? On the other hand, you haven't had much time to look at it, but you have had time to think about it already. So you might think about what you did, think about what I did, see if you can come up with some other way of doing it. Let's see, I can take a quick look at the chat and just see what we had there. Who was it that was saying you had something? Oh, yeah, this little thing. Let me see. Oh, wait, okay, hold on. So this, we have this, and so we're saying, and what do I know? Let's see, at this moment, I'm showing, we're trying to show boundedness, right? So that this has to be greater than or equal to that. Oh, actually, yeah, sorry, let me pull this down here. Yeah, who is it that, so this was, who sent this in? Wait, how do I get this to come down? Oh, shoot.
Hugo sent it in.
Okay, hold on. So Hugo may have a much simpler argument here. Let's just bring it down here and look at it. If I can get it to come on down here. Okay, so there's his argument here. So let's see, the assumption at this point is that alpha n is greater than or equal to alpha, right? We're trying to show that xn is greater than or equal to alpha. We're trying to show that xn plus 1 is greater than or equal to alpha. Or he's calling it an, so let's just call it an, right? Trying to show that an plus 1 is greater than or equal to alpha. So here's our inequality, right? And so this is the same inequality. So that's, oh yeah, so I mean, this is exactly what we're looking at too. So yep, this is nice. This is so much better. Yep, so there we get the multiplication and we get that. And it's so much easier than the crazy thing I did. And this is beautiful, yep. So I need to incorporate this into my, so I will completely erase my notes and put that, and I'll credit Hugo for it. That works out really nice, actually. And it is exactly the formula we're starting with. Yep, so good. So you see, you can go down a path, and there are always different ways of doing things, and there was a different way. So kudos, Hugo, for that. Good. So, gosh, Hugo, if you had just said that 30 minutes ago. Good. All right. So, well, I mean, it's good to go through the whole argument anyway, but excellent job. Any other questions about that one, right? So this is like just one of the problems.
Isn't that the whole point of the difference between real analysis and calculus, is that in real analysis, we're going to have to do exactly what you just did versus what Hugo did, which is how it would be done in calculus?
No, he's doing exactly the same thing. Like I used what did I do? I did this kind of brute force calculation until I got it into some form. I mean, let me just give you my thinking again about it real quick. Like I was trying to just do a boundary.
Before you go down that rabbit hole, Dr. K, I love it, but I don't want to take anybody else down there because I know I love it. I'm just trying to really understand the distinction between real analysis and calculus, because when I was doing my research, calculus was about computations, whereas real analysis is using general and ambiguous and not being so precise. It's like you're proving the proof.
Yeah, that is I mean, we did that here, right? So I mean, one thing we did at the end here was we actually proved that every decreasing bounded sequence has a limit, right? So I mean, that's an actual proof that you will do in the analysis class, right? This was a decreasing sequence. An increasing bounded sequence also has a limit, same proof, right? So the theorem you'll get is any monotonic bounded sequence has a limit, right? So that's this theorem here. The other thing we did is in that vein, right, is we didn't just go from this kind of sloppy calculation, which in the end does work, right? Alpha over xn, right? So I said, just take these limits. So this is very calculus-like, right? You just put L there in 1/2, L plus alpha over L, right? And set them equal and then solve. and get that L equals square root of alpha, right? So that's just computational. What we did here is we did the extra step, right, where we actually showed that this thing was a decreasing bounded sequence, and so that limit actually existed, right? So that's like the real analysis part, right? So that's the difference, right? Okay, good. Let's see. Same kind of thing here, the radius of convergence. I don't know, has anyone tried this one? I don't know. Hugo, did you come up with a better way of? Like, I think the basic part is, okay, so I think part of it is pretty straightforward, right? When you're trying to use the ratio test. By the way, here, in order to use the ratio test, you might have to look up what the ratio test was, right? To see what it was. Right, and so it's you just taking like an is that expression there, right? So if you take an plus 1 over an absolute value, right? You just, that's what you get. You do some algebra on it and you get that expression there, right? And then here you have to apply a little bit of calculus, right? Because here we're taking a limit, you know, the limit as n goes to infinity of n over n plus 1, right? What is that? By the way, what is the form of this limit? Oh, sorry, to the nth power, right? Sorry, to the nth power. So like n over n plus 1 as n goes to infinity is getting close to 1, right? And it's a little bit less than 1, right? So what's something a little bit less than 1 raised to a very large power? Well, it's something getting close to 1, right? Maybe, right? Or something getting close to something, right? Maybe. What is it?
E, right?
So in this case, it turns out to be 1 over e, right? This one turns out to be 1 over e, right? But now there's this calculus stuff that comes in. How do you actually compute that limit? So there is kind of two ways. So I mentioned this in the notes. If you look at the opposite of this, if you look at 1 over this thing, right? So if we look at the limit n goes to infinity of n plus 1 over n to the n, right? So this is the same as limit n goes to infinity of 1 plus 1 over n to the n. And if any of you teach like financial math, right, you might sort of recognize this. Like if we're looking at putting money into a bank and accruing interest, right, where you're doing it n times per year, right? So like the future value of an account, right, would be like this. And this, by the way, is a geometric series calculation you would do. So one way of writing this would be exactly this ratio here, right? 1 plus 1 over n to the n raised to the t power, right? So like that. So the only place where the n comes in, how many times you're compounding, is right in there, right? And so you might know that if we let n go toward infinity, we're looking at continuous compounding. So that might be one reason you know that that's E, right? Maybe, right? If you sort of followed all that stuff through. If you happen to teach financial math, right, or even maybe sometimes in pre-calc or algebra 2, you do something like this, right? More generally, we would use calculus, right, for this purpose. And so this is a place we're using derivatives to do something kind of fun. So the original one was like this. To the n, right? We're trying to take this limit. And so what you often do when you're looking at and by the way, you have to recognize this has the form 1 to infinity, right? And that is actually one of the indeterminate forms. So you know that that's not, you don't really know what's happening there until you do some more work on it. Indeterminate forms like infinity over, I guess infinity over infinity, 0 to the 1. I'd have to think exactly what all the indeterminate forms are. Infinity minus infinity. I mean, you don't really know what these things are until you start doing some analysis on them. And a thing you can do here is replace the n, which is a discrete variable, by x, right? So in terms of taking a limit, this is the same. All right, so like that. And then you'd like to set this up to do something with L'Hopital's, right? And for that, you need like a product, or you actually need a ratio of some sort. So a natural thing to do would be to take the logarithm of both sides, I guess, right? And and then I guess here's where the real analysis, actually a calculus question too, comes in, is why does that work, right? So what I'm going to do instead is take the limit of the natural log of this thing. X goes to infinity, right? And part of the reason that this works is because this is continuous at the place where this limit actually has a value. This is the same as the natural log of the limit as n goes to infinity of x over 1 plus x to the x, right? So we're actually using, in order to take this limit from outside and put it inside, we're using some continuity, right? So this is stuff where you need to apply some theorems from real analysis, right? Here I'm just gonna use it. I'm going to concentrate on this side now, right? So I'm trying to turn it into a calculus problem. So this x goes to infinity. So this turns into x ln x over x plus 1, all right? And the next thing I'd like to do is kind of, let's see. So I really like the ratio in the other direction. So I'll pull a minus sign out, right? So this is minus lim x goes to infinity of x ln x plus 1 over x, right? If I flip this over, right, I can pull a minus. That's like this to the minus 1 is that. But if I have a minus 1, natural log something to the minus 1, the minus can come out. So I'm using some algebra here for this, right? And then in this form, right, I can rewrite this as this. So this is minus lim x goes to infinity of x ln. So this is looking like that form I had before, 1 plus 1 over x. And finally, this is, now I want to turn this into a ratio. Again, I'm trying to use L'Hopital's rule, right? And so this is going to be, let's see, I want ln 1 plus 1 over x over 1 over x, right? So now it's like that. Now we're sort of there. So now this is a ratio. This is going to 0. That's going to 0. So now this has the 0 over 0 form, right? And so it would be natural to take a derivative of both sides and try to apply that. But here it's actually even more useful to change this to limit. If x is going to 0 plus, right, then 1 over x, sorry, to infinity, 1 over x is going to 0 plus. So I can replace this 0 plus ln of 1 plus h over h, right? And you might say, gee, why is that valid, right? I mean, it's kind of clear. I mean, you could just do an epsilon, and I need a minus sign. You could just do an epsilon delta type proof for this thing. But I am, sort of swapping out one function that has a limit for another thing with a limit. So really there's sort of a, if you like, a real analysis theorem there. Once I have it in this form, finally I can use L'Hopital's rule, right? So finally I can just do the calculation, so to speak. And so the point there is if I have a limit of something like this, I can turn this into the limit of the derivatives of these things, right? So this can be the limit h goes to 0 plus of the derivative of this thing up here, which is 1 over 1 plus h, over the limit as h goes to 0 plus of the derivative of this, which is 1, right? And so this is finally minus the limit h goes to 0 plus of 1 over 1 plus h. And of course, that just goes to 0. So this is 1. So, sorry, minus 1. So we are using a bunch of limit laws along the way. And going way, way back up to the top. So the limit of the natural log of the thing is minus 1, right? So the limit of the original thing, x goes to infinity of 1 over, let me have to go back and see, x over x plus 1 is e to the minus 1, right? Which is 1 over e. All right. So I mean, so it's kind of fun because you have to do some calculus stuff along the way, right, to get this limit. And I talk a little bit about how you can move the limit signs between these two things. And so when you're done, right, you have that an plus 1 over an is equal to e to the minus 1 x. And now for those of you who remember your calculus, when is this thing going to converge? So I've done the ratio test. So when is it going to converge? When this limit, first of all, the limit has to exist. In general, there's no reason the limit exists, but if the limit exists, so here it exists, and it's going to converge if this limit has value less than 1, right? So that's when it's going to converge, right? So that's the ratio test, right? So in particular, it's going to converge when the absolute value of x is less than e, right? And so now we have the series summation n factorial over n to the n, x to the n, n equals 0 to infinity. So let me call this p of x, right? It's kind of like a infinite power series in x, right? It's like a polynomial, but with, you know, letting powers go all the way up to infinity, so to speak, right? And so what we know is we know that this thing, p of x, defined this way, right, is defined. So this thing converges absolutely, right, for absolute value of x less than 1. Is defined for x less than 1, right? So those of you who teach calculus, this is a very in fact, if you went and grabbed your problem from the AP calculus exam, you may have grabbed one something like this. Probably not this complicated, right? Probably not with n factorial over n to the n, right? But this one's kind of fun for the next reason. So the radius of convergence, right, is the interval of convergence is minus, sorry, not the interval. The radius of convergence is e, right? So the interval of convergence may or may not contain one of these endpoints e, right? So it might be minus e, right? It might be minus e this way, right? We don't really know yet what it is. It might be minus e, right? It might be just the interval we already have, right? So the question there is, does this thing converge at e? Does it converge at minus e, right? So in other words, do these things converge, for example? Does this thing, so this is n factorial over n to the n minus e to the n, does that converge? Does this converge? N factorial over n to the n e to the n, right? Does that converge? Right? And it turns out actually that these terms, doesn't matter which one of these terms I look at, let's call this an, all right? And this is, you know, this kind of goes back and forth between plus or minus, right? Depending on n, right? But we could call this, you know, I'll call this bn, right? Neither of these things actually go to 0, right? And for a series to converge, the terms actually have to go to 0, right? So it turns out that this series does not converge at the endpoint. So the entire interval of convergence is this thing here. And so things you'll learn in real analysis, of course, is like, now that we know it's convergent there, what do we know about the derivative? What do we know about the integral? What are their radius of convergence, interval of convergence, all this sort of stuff, right? So I mean, that kind of stuff will be talked about some in 571 too, just all the theory involved in that. This one's fun because to check that this doesn't go towards 0, I'm just going to write it over here. We have to use this fun fact, which is definitely a real analysis fact, called Stirling's formula that says, whoops, 2 pi n. To the n, right? So if I wanted to try to approximate n factorial in a way that just uses standard functions, square root, multiplication, powers, this, right, is a good approximation of n factorial. That's like totally surprising, I think, right? So that's a nice bit of math there. I'm not telling you why it's true. I'm not going to go into that right now, right? But that's a nice, interesting thing right there, right? So called Stirling's approximation. But if you take this Stirling's approximation and you put it in for n factorial in these places, you'll see that these terms do not go to 0, right? And so therefore the series cannot possibly converge, right? So that's kind of fun. Anyway, we're about out of time. Yeah, go ahead.
You've mentioned in across the last 4 weeks a lot of different, just like you just went over Sterling and you went over the one right before that, the AA, the AA, and there was another one that you went over. Are these concepts that we need to have some kind of mastery over before we get to our next classes, or should we expect
No.
someone to teach us deeper, to a deeper understanding of it?
I mean, the point of this class is to show you what you will see going forward, right? Not to show you what you should know. That would be kind of boring, right? So the point is to show you what you will see, right? And
So
kind of
deductively,
sorry,
so
let me just say one more thing.
deductively thinking, I'm sorry.
Yeah.
So deductively thinking, if you're showing us something that we're going to learn, then
Yeah.
technically you could, I'm just using the reasoning skills that I've gotten. The true, false, false, true, my bad.
Mm-hmm. Sorry, I mean, yeah, I mean, the point is I want to show you things at the level you're going to see them, right? Trying to hit on things that still you kind of should have some idea about, right? I mean, this is you know, the ratio test and convergence of series is something that you should have some idea about, right? So I mean that's definitely like Calc 2 level stuff, and that's definitely the prereq coming into the class, right? But then I want to give that in a context where you're going to see it at the level you might see it in, you know, in the real analysis class, right? Now this is still pretty much calculus type stuff, right? If you really want to get a better view, you know, look at the actual notes that I made here. There's a lot of stuff in here, and again, there's a lot of stuff here wouldn't expect you to know, but I do talk about continuity in general and open sets and neighborhoods, and what the sort of the correct way to say a function's continuous and continuous at a point. And I also talk about connected and what that has to do with the mean value theorem. So there's a lot of stuff here that is stuff that's exactly like what you will learn in the real analysis class. So you can sort of look at that and see if you can understand part of it, but you will also get a good idea of like the level of generality there. And there's a nice application here too. So here I've got a function which is going from the sphere, right? S2 is like the usual sphere, like the surface of a basketball, to the reals, and it's continuous. And I want to show that there are 2 points directly antipodal from each other. So on 2 opposite sides of the ball that have to have the same value of t. Think of t as temperature, for example, right? So that's a nice little application of this kind of should have called that. I mean, that's the intermediate value theorem. Actually, I may have put I think I got this this corollary is in there. I need to move it back up to where it belongs. So that's actually the intermediate value theorem. What did I call this mean value theorem? I should have called this intermediate value theorem. Sorry, not mean value. This is not the mean value theorem. I just have the wrong name on this thing. I need to change that. And then I also described the sort of topological way of saying what compactness is.
Last one, may I let you go?
Sorry, what's that?
Tomorrow may have radiation.
Oops, someone's got some sound back there.
Oh.
Right, and then this last example here that I have in the notes, there's a lot of stuff you probably will not understand there, right? But it's a nice, this, like I said at the beginning, this is a nice theorem that would be a good thing to shoot toward fully understanding at the end of 571, right? So that's a thing. And I forget, one of you has a maybe it is Hugo anyway. One of you has a math background already, right? Like already has like a bachelor's or something. Was that Hugo?
I do.
Oh, you do. Okay, so Beverly has a degree. So I
I
mean,
also have the like science of mathematics.
Yeah, I have a BS in math as well, but that's been years ago. So
okay. So I mean,
Same,
you
but
might
years ago.
you might find some of this stuff rings a bell to things that you've seen before, I imagine, right? Depending on, yeah. So so anyway, I mean, yeah, I mean, all of this is meant to be things that you will, you know, be looking forward to. Anyway, we're about out of time now, and this is our last meeting, so it was great meeting all of you. Hopefully I can get some things graded. We'll see what actually ends up happening. Either way, it was, you know, all of you have been good students, and I think you should enjoy. So your next class will be the history of math. I won't be teaching that. I might be teaching your algebra class when you get to that, maybe. Depends on how the schedule works out. Or I might be teaching the linear algebra class, or even 571. I mean, I guess those are still a ways out there. Ben will be your, who's actually the department chair, will be your history of math teacher. So anyway, it's a fun class. Try to have fun with it. It's not a super hard one yet. It's not one of the serious classes yet, but it can be serious. I mean, it's depending on what he does, right? There can be some serious math there, but it's not a single subject class. I mean, it is a history of math class, right? So there, you will study things like what the Mayans did with numbers and Egyptians and stuff. But there's actually a surprising amount of stuff to do there, right? And even when I did it, we read through like part of Euclid's book, right? Euclid's geometry. We like took that and actually tried to prove theorems in the method of Euclid, which was kind of fun to do. So there's lots of things you can do in that class. But it will be a different sort of class in that sense, right? Anyway, any last questions before we say bye and see each other in the future?
I did have a question on how would exams work, like being like an online class?
So that will depend on the person doing the class. So the way I do it is I give fully take-home exams. So like my 513 class right now has their exam. When we meet tomorrow, we'll talk about any issues on the exam. That's mainly what we'll talk about. And they have a full week. And again, the way I do things is I actually let them do corrections. So I give them the solutions the day they turn in their exam. And then I let them have a couple of days to do corrections and reflect. I actually think that's a good thing to do, is to let them see where they made mistakes, correct their mistakes, and then kind of reflect about why it was that they made that mistake. I think that's kind of an interesting thing to see. That said, they being completely take home, they can be a little bit on the tough side, right? Because I know they're going to use sources. They may use AI. There's all sorts of things you can do these days, right? So the problems are such that when I see their solutions, I can say, yeah, that looks like something they understood when they wrote it, or that looks like they're just copying something from an AI, right? So you can tell usually when people are writing up solutions. So I mean, the one thing I would say is stick to the stuff you're learning, right? Be prepared to completely justify anything you do in an exam, right? So like, don't go grab some fantastic theorem that you don't know anything about and apply it as solving a problem to an exam, right? Because I'm going to look at that and say, that looks like it was just copied. I may contact you and say, okay, you can use this if you can completely tell me why this thing you used is true, right? Usually that's not the case. So, I mean, that's the one thing the one, at least in my classes, and I think a lot of them, you'll have take-home exams. They won't be easy. They won't just be simple computations. They're going to be some theories. You're going to have to do proofs, right? I tend to give some true false and ask the students to justify. So there's like some credit for the true false, some credit for the justification, right? So a lot of the theory gets sort of built into the true false part of the test and the justification part. And I feel like usually I get a pretty good feeling for what the students know. So I mean, even though in my class they're completely take home, I think they do what they need to do, right? So again, different people will do different things, but that's kind of how I do things. And I will say the 512, 513, and 571 are all courses that I've SME'd, which means I was the one who, picked the material and the way it's structured and things. And so those courses have 3 weeks of material, and then basically a week of testing / project where you're taking your test and working on a project, where there's no new material, or maybe if there needs to be a little bit of catch-up time, right? And then another 3 weeks of new material, and then a final week of exam plus catch-up time / project. Some of the courses have multiple projects in them. The projects are usually teaching-like projects. You'll make up something related to the material that you would give to a class, right? Or maybe even give to each other as a class or something like that. But that's generally the structure of those classes. So there are these kind of week 4 and week 8 in those classes, while they are exam weeks, tend to not be giving you new material, right? So that should be a good thing. The other class that's brand new is the statistics class. So I really have no idea how that one's going to run when it runs. The class which is 550. Oh yeah, anyone who needs to go can go. Yeah, sure. The class that's 550 is kind of an amalgamation of two classes that used to be separate classes. So I'm not completely sure how those two classes will go, but those two classes I don't teach anyway. Those are outside of my subject area, so I won't teach those. You had a question, Crystal?
Yes, sir. I was just going to say that, is there any way for when you share your notes for you to invert them so that the background is white and the ink is black? Because when I printed it, I used up all the ink in my printer.
Oh, God.
I just do a better job. Once I've heard you watch the notes and then I go back over your notes and I rewrite the notes in my notebook, it's easier if I'm going from paper to paper than just looking at the screen. But when it's black background, that's a whole lot of ink.
Yeah, right. So it's probably something I need to do before I save it and convert it to PDF. So let me just make a note of that. So swap background.
Thank you.
Yep. Okay, I will do that. I think for the presentation it's good like this for seeing, right? I feel like it's good for seeing like this. But then I understand what you're saying about the printing. Of course, you could just save the PDF and look at the PDF too, but I will swap it for you to do whatever you want to do with. Yeah.
I read the PDF, but it's like looking at a textbook sometimes, and I'm dyslexic, not gonna lie. So it's like sometimes it's just easier to go step by step and hear your voice in my head when I'm looking at your notes.
Okay.
And that's all I'm saying.
Okay. And then Tringle, you had a question?
Yeah, I was trying to compare what I did on this third problem that using the ratio test. I'm wondering where you got to the end power on the third thing, because when I do the ratio test, I just get X, or the absolute value of X. And I don't know.
Yeah, we can look at that real quick. So I mean the initial expression is this. Right? This is just the two ratios, right? Do we agree to this point?
Yes.
Okay. So then yeah, and then of course there's x to the n plus 1 over x, and there's absolute value, so that just turns into x, right?
Right.
So that's like that. And so now what happens here? So here's what I didn't write, right? Is this is n plus 1 n factorial. That's the n plus 1 factorial, right?
Right.
N to the n over n factorial. And then down here, I'm going to pull out another n plus 1. And then I have n plus 1 to the n.
Okay, right? Where are we pulling out that n plus 1?
Because that's coming from here.
Oh,
this is n plus 1 to the n plus 1.
I see and
where
I made my mistake.
These are canceling, right? And you see it now?
Yes, I see where I made my mistake, what I missed. Thank you.
Okay, cool. Yep. And let's see, and then Melissa has a question too.
Is there like a way for us to get like tutoring for like our next classes? Because I start my next class and I was looking at the stuff that we were going to be given and I was just like a little confused. So is there like a way for us to get tutoring, or like that's just something that we have to find on our own for those classes?
So first of all, I'm not sure. Yeah, I really don't know how tutoring at this level would really work. Are there good tutors? I really don't know. This is the history of math class you're talking about now, right?
Yeah, I was looking at week 8 and there was like something with Math Lab, and I know that I've been struggling with Math Lab right now. So I was just like, oh no.
So so I'd say one thing you could do is, I mean, one thing is you will know us, right? I mean, I wouldn't want to become the tutor for everybody, right? But if you have a MATLAB question, I don't mind you sending me a question about MATLAB. So if you want to, right? In my class, I think I gave this to you at the beginning, I let people just sign up for meeting times. Like Crystal did that once. So only one of you did it. So as long as it's not crazy number of people, then that's a good thing to do, right? Then so you could just use that. I don't really know that. I don't know that Ben or who's the next teacher will do that. I think that the MATLAB in that class is probably going to be a pretty straightforward template, and it might. Yep. Okay. So yeah, anyone who needs to go can go, and any. And it might even be skipped. I'm not even completely sure that they'll do it in 525. That particular MATLAB assignment. When you get to the linear algebra class, there'll be a whole bunch of MATLAB, but it will all be templates where you're filling out templates that are pretty much telling you what to do. So I think that won't be I think the math itself will be harder than the MATLAB. Right.
Okay.
And then there's other things too. I mean, this is one of the things AI is really, really good at, right? Is coding. And so when I want to do something new in MATLAB, I usually start by asking chat, how do I do this in MATLAB?
Okay.
So, I mean, that's definitely something you have now that you didn't used to have, right? So I'm not sure I would worry too much about getting tutoring for the MATLAB part.
Okay.
I feel like you can get help from the teachers and from other sort of sources like that. At least I wouldn't pay for tutoring for the MATLAB part. And of course MATLAB itself has a whole bunch of, like, we had you do one class, but with your access through the campus, you have access to a whole bunch of learning materials in MATLAB, including lots more like little courses and stuff, right? So there's lots of stuff there. So. Yeah, I'm not sure I would worry about I don't think any of the coding is going to be such that, like, you're never going to be tested on coding or something, right? So I wouldn't let that worry you too much.
Okay, thank you.
Yeah. Sure. Okay. Anyone else, or otherwise I'll say bye and I'll see you again in the future. Let me see. Maybe I can turn my.
Hey,
I can turn my camera back on and
Dr.
wave
K,
at you.
I wanted to say to you that I noticed that you use Desmos a lot, and when I started trying to practice with Desmos and vectors, I found out that Desmos geometry will let you actually use vectors, and all you got to do is turn on all your grids, and it turns into the exact Desmos, but it gives you the added effects of geometry with it, and it's much better than regular Desmos. So I don't have it mastered, but I just saw that you've been doing a lot of Desmos graphs, which I appreciate. But I thought that maybe you'd like to know that because you didn't really like Desmos that much. But Desmos geometry is better than Desmos by itself, and it's free.
I guess the last time I tried that, the vector one, I have only used in 3D. So I didn't, like, for example, on the example I gave you today. I mean, let's look at this one, right?
Move right, yeah.
I think it does. Let me see. So let me go find that one again.
The one with the curve.
Yeah, let me open this up because this one did take me a little. So now there is restrictions because of the way. So here's like you can't take it too far out of it, right? But it kind of does what it's supposed to do there, right? And you can see it's kind of moving through the field, right? So that part was okay. The thing that was really a pain, the little this is where the vector field would be nice, right? Because here I have to draw these lines, and I have to just do this over and over and over and over and over, right? To like draw these lines one row at a time. Right, that's a pain. So if the geometry thing could do, like, give me a vector field of, like, for the derivative, right? That would be nice. I mean, there's also GeoGebra, which can do some of this stuff, but there's always playing around, right? And I could have done this in MATLAB. The thing about MATLAB is I don't have a way, like, I wanted you to be able to do like play with how far you took it, right? Do that kind of thing and move this sort of in real time and look at it. And I don't know how to do that so that it works very well in MATLAB, right? MATLAB is better at static images than things that you kind of play with.
And right. I enjoyed that. So thank you for the effort that you put into that. Seriously.
Oh yeah, I mean, I'll use it again. But
I just wanted to throw that out there because I found, I don't teach, the highest I go right now is Algebra 2. Next year I teach pre-cal, but I just really enjoy using images to help my students make connections to the math. And when I saw that curve with the vector fields, I was like, yeah, that's nice. That's really nice.
Let's see. Let me. There's a funny one for transformation of graphs for pre-calc, right? I have this thing where you can stretch, change the stretching and shift, right? This is funny.
Yeah, that's nice.
Yeah, I use it all the time for just little things like that. It's kind of fun to use.
It is.
Yeah.
But hey, I've enjoyed you. See you in the future, Dr. K.
Yep. See ya. See everybody. Bye.
Bye.
See you, Hugo, Beverly.
See you in the future.
Yeah.
But we have him again.